Hi, welcome back. Today, we're going to talk a little bit more about entropy and kind of go a little deeper into the entropy kind of phenomenon, if you will. All right, so we have entropy and state change, the concept. So, how is entropy changed as water moves from a solid to a gas or solid ice to water vapor? So, let's look at that kind of first on the particulate level, and then we'll talk about the entropy of it. So, going back to our particulate diagrams, we're going to draw three of them. All right, and we're going to start with solid ice, right? So let's make those little X's kind of like we've done before. Then as we start to get it to change to water, remember it's kind of in a little haphazard, and then water vapor, we're spread evenly throughout the container. All right, so what we've done here, remember entropy is the measure of microstates. So as we go from here, we have very few microstates. Very, very few microstates. There is some vibration there between our particles, but not a lot. So we really have just vibrational energy there when we have a solid. Then as we move into our liquid, we start to get a little more energy, right? And we have a little more motion. We have both rotational and, mainly rotational and a little bit of translational, right? As well as translational, all right? We still have that over here. We had vibrations, right? Here we still have vibrations, right? Vibrational. And over here we have vibrational, right? And here we have rotational, translational, and as well as just kind of floating around, right? This is just like kinetic energy, right? So we have got a lot going on here. And so there's way more microstates if we think about it. So many more microstates. All right, we have a ton more microstates in this one. So our entropy is increasing because we have so many more microstates because the energies of the particles is so much different. We go from just vibrational to having both vibrational, translational, and rotational. All right. Okay, awesome. Now, so if we think of that, thinking of it in terms of having many versus a few, if we do final minus initial, our sign change would be positive, right? If we go from, if our final is a lot, say 1,000, just for an example, right? 1,000 there versus 2, 1,000 minus 2 is a positive 998. Right? So that's what we're talking about. So we're thinking when we have an increase in entropy, we have a positive change. All right. Awesome. There's also another way that we can do this. We can calculate entropy another way, and this takes us back to our thermodynamics, right? So we have delta S is equal to Q of the reverse reaction, right? Q of our reverse. So we're talking about a reversible reaction as well, right? Okay, which also equals, and remember this, it also equals delta H. We talked about that over our T. So that leads us to our label on entropy. A lot of time our label is joules per K. All right, joules instead of kilojoules. That's the tricky part. Joules instead of kilojoules. And so later, when we probably in that next section, when we talk about free energy, we have to talk about kind of putting them together. So that's the tricky part. We have joules instead of kilojoules. And remember, our reversible processes are our equilibrium processes. So please don't forget that, but we just spent a ton of time doing that. Okay, so finishing this up, an exothermic process increases the entropy of the surroundings. All right, an endothermic process. Oh, let's finish that. Sorry, I missed that last part. An exothermic process increases the entropy of the surroundings because we are releasing energy, right? Releasing energy to the surroundings, which is going to cause them to move more and have more microstates. So let's kind of do that. So more movement, more microstates. Beep. More microstates. All right. So now an endothermic process, which absorbs it, right? It decreases the entropy of the surroundings. All right. Because it is taking in energy. Which obviously slows those particles down, right? And giving it less microstates. Okay? So then the question becomes, how do endothermic processes occur? Because remember, our law of thermodynamics, right, says that something is spontaneous, right? But our endothermic, since it's absorbing energy, it is taking in energy, and the system, instead of the surroundings, is absorbing energy, right? We know that, right? So thus the system is gaining entropy. All right. And all it said for a spontaneous process to happen is we had to have the entropy of the universe increasing. So if something is increasing, then we're good to go. Awesome. See you on the next one.